Hello, everyone. Thanks for joining us today. Today, we have our guest speaker, Carolina. Calarina Muslimani is a fourth-year PhD student at University of Alberta in reinforcement learning and artificial intelligence lab, advised by Matt Taylor. Our research focuses on designing human-aligned reward functions for reinforcement learning, including developing metrics to evaluate reward functions and creating reward learning algorithms. Uh, Calarina, floor is all yours. You can get started.
Awesome. Yeah, so thank you so much for that introduction. I'm really excited to be talking to you all today. So today I'm going to be talking about our recent RLC work titled Towards Improving Reward Design in RL, a reward alignment metric for RL practitioners. Now, throughout my talk, I'll have some slides where I'll stop to see if people have questions. Otherwise, you can also ask questions at the end of my talk. Okay, let's get started. So I'm going to first outline the three major topics for today. So I'm going to first rant a little bit about reward designs being really hard, and I struggle with them a lot. But I'm also going to talk about what makes them challenging. Then I'm going to talk about reward evaluation. So once you have a reward function, how do you know or identify whether that reward function is properly specified or properly specifies your task of interest? Because that can also be difficult. And then I'm going to end with talking about how we can improve reward design. So if this is a really challenging process, are there things we can put in place to make this easier for our practitioners? Okay, yeah. So as I said, I'm going to start my talk by complaining a bit about kind of how I've struggled with designing reward functions in my kind of current state. Okay, so this I feel like this kind of sums up my life. So this is a character from Always Sunny in Philadelphia, if you've watched that show. But yeah, as Rahul mentioned, I'm a fourth-year PhD student, and so I've been studying reward design and reward learning for, I guess, the past like 3 years now. And in that time, it seems like I have all types of questions, but it feels like never enough answers. Like I'm just always confused. So for instance, how do we design reward functions? Are there protocols or processes that can make this easier? Should we be looking at designing sparse reward functions or dense reward functions? At my university, at the University of Alberta, I feel like there's always this debate, oh, maybe we should do sparse and focus on better algorithms and kind of that back and forth. Well, what about reward learning? If manually specifying a reward function, if that takes too much time, maybe reward learning is a better alternative. And even more from a high level, more like a philosophical point of view, where do I even think rewards come from? Do I really think the environment, like this separate entity, gives the agent a reward? Or maybe the agent has its own like reward mechanism and it kind of creates its own reward for itself. So yeah, I feel like I have lots of questions, but kind of throughout my PhD, I'm aiming to at least answer a few of these. Okay, so of course, if we're going to talk about rewards, we have to talk about the reward hypothesis. So my guess is many of you have seen this, but I'll quickly read it. So it goes like this. All of what we mean by goals and purposes can be well thought of as the maximization of the expected value of the cumulative sum of a received scalar signal called reward. And so this is from very early in our textbook, page 53. Make note of how early we learn about the reward hypothesis when we are studying the RL textbook, because later on I'll come back to that. Now, we may all, I guess, agree or believe in the reward hypothesis, but really I want to talk about kind of my interpretation of it. So when I think about the reward hypothesis, it seems like it's telling me that there exists a reward function such that if our agent maximizes the cumulative sum of it, then our agent, excuse me, will accomplish the intended goal. But I guess the emphasis here on there exists. So for me, it seems like the reward hypothesis is like an existence proof. It's saying like somewhere out there in this, like in the far abyss, there is a reward function such that, and if I find it, like good things will happen. I can do RL my agent will have a good policy and everything is great. But that seems not really satisfying to me, because what does the reward hypothesis not tell us? It doesn't tell us how do we go about designing this reward function. How do I find this reward function such that kind of good things happen and that I can actually do reinforcement learning. And kind of even more so, I feel like the joke is on us. Well, it's definitely on me. So this is another snippet from the very end of the RL textbook I also wanted to read to you all. So this is how it goes. The parts of our brains that generate these reward signals for us humans evolved over millions of years to be well suited to the challenges our ancestors had to face. We should therefore not think that designing a good reward signal is always an easy thing to do. So I recently came across this snippet like earlier this year, and when I saw this, at first I was thinking like, dang, I hope it doesn't take me this long to design a reward function for my task. But then second, it feels a bit ironic. It's like without the reward function, like reinforcement learning just breaks down. So why did Andy and Rich have to wait until page 469 to talk about how hard designing appropriate reward function is? Why couldn't they have kind of told me this earlier on in the kind of in the textbook, so that it would seem like a more important problem? But maybe it's my own punishment for taking me like 4 years to get to page 469. Yeah, so I digress. But okay, all jokes aside, like why is reward design such a difficult process? And first is that often when you're doing reinforcement learning for a real world application, it's really collaborative in nature. So you might have a domain expert that has specialized knowledge of your task of interest, and they might be communicating to the oral practitioner preferences, constraints, desired outcomes, kind of, etc. And then it's up to the oral practitioner to design this reward function that satisfies all of these constraints, preferences, etc. And this kind of back and forth can make this more challenging. The second is that when we're thinking about reward design, we have to think about the return. And that might seem obvious because, of course, we're maximizing the return, we're not maximizing the reward. But it seems like actually a non-intuitive process to think, how do my individual rewards affect kind of the total reward? So for example, if I have a trajectory of length 1,000, how do, let's say, like the early rewards affect the total reward I will achieve? And so I think it's not always intuitive. So I want to walk through this quick 5-state MDP to kind of emphasize that point. So yeah, let's imagine we have this very simple 5-state MDP. This is going to be a continuing task so that the kind of episode never ends. The agent, let's say, starts in the green state, S0, and it can take actions going left or going right. If the agent enters either of the red states, then it'll automatically reset back to the start state in green. Let's say that all the rewards are 0, but it will receive +2 if the agent enters the red state S3 on the left, or if the agent enters S4, it'll receive +1 on the right. And let's consider a discount factor of 0.99. Now, when I was making this MDP, I remember me and my advisor, we were going back and forth because initially we were thinking that going left would be a better policy because we get +2 and 2 was bigger than 1. But actually, when you take the value of these two policies of always going left or always going right, actually always going right and collecting a +1 reward is a slightly better policy. You do get a slightly better long-term return. And so this is, again, one simple example of how reward and return, they don't always kind of go hand in hand. And this is a very simple 5-state MDP. Imagine when we're considering more complex tasks and more long horizon tasks, this can only make it more challenging. Okay, I'll stop here to see if anyone has any questions. But if not, I'll just continue to move on. Okay, I'll continue. Okay, so the next major topic for the talk is about reward evaluation. So given that we have a reward function, how do we evaluate if our reward is properly specified? How do we know whether if we do RL on this reward, we're going to have a good kind of behavior at the end? One very common approach to this is something called trial and error reward design. So if anyone in the audience has designed a reward function, you've probably kind of done some process like this. So you have your first kind of candidate reward function, you train an agent with that reward function. You then, after it's done training, you look at its policy, you ask yourself, do I like this policy, do I not? If you don't like it, you go back and you adjust the reward function in some manner. Then you go train another RL agent with that reward function, and kind of so on and so forth until you think, okay, you have like a good enough policy. Now, there are several things kind of wrong with this scheme. The first, maybe most obvious one, is that this can be very expensive. So one, it can take a lot of time. So if you're training for every single reward function, you have to train a new RL agent. And for some, even for, let's say, like DeepMind control or Mojoko environments, this can take like 8 to 12 hours. So this could take a very long time to end up kind of getting the reward function you want. And of course, it's also requires a lot of compute, so a lot of GPU or CPU in order to continue training. So that's kind of problematic. The second is that this process can result in reward overfitting. Now, this is where your reward function can become unintentionally over-engineered to a specific RL algorithm or environment instance. For example, suppose you're tuning your reward function based on the performance of a DQN agent. What can happen is, if you decided to then use that same reward function, but now use a soft actor critic agent, it might end up failing. Like your soft actor critic agent might not be able to learn a good policy with that reward function. And this is an issue because now our kind of reward functions become very dependent on our algorithms, but really the reward function should be agnostic to that. And lastly, this process is not really applicable to the online RL setting. And that's because it really assumes this distinction between training and deployment. It assumes we have access to the simulator. I can train a bunch of agents on different reward functions, and then okay, when I have a good one, I'll go deploy that. But in the online RL setting, we don't have this clear separation. Okay, so if we can't use trial and error reward design to kind of create reward function, what's a better alternative? So in this paper, we were thinking about, okay, how about we use reward alignment as an evaluation scheme? So what that means is we're looking at or trying to answer the question, does our reward actually encode the preferences of the human stakeholder or domain expert? Now, if we're kind of in this more real-world RL setting where we have our domain expert and our practitioner and they're collaborating together, we want to ensure that the reward function we design respects all of the domain experts' preferences and constraints. To operationalize that idea, in this paper, we propose a metric we call the trajectory alignment coefficient. And at a high level, the idea is that we want to be able to evaluate the similarity between a human stakeholder's preferences over a set of trajectories or trajectory distributions to those induced by a given reward discount factor pair. More specifically, this metric is based on Kendall Tau B, which is a measure that looks at the level of agreement between two sets of rankings. So if we have our human rank a set of trajectories, and then we also get a ranking from our reward, we want to see how similar they are. So if the rankings are identical, then our score would be 1. So this would be the best case, like strong alignment. If the rankings are reverse, then we'd end up getting a coefficient of -1, and this would be the worst case misalignment. So this trajectory alignment coefficient produces a score between -1 and 1, kind of indicating how well your reward discount factor respects the preferences from your domain expert. Okay, so I know so far I kind of described this metric at a high level, but over the next couple of slides, I'll walk through an example of how we can use this metric in a very simple autonomous driving domain. So the first step, if we want to use this metric, is of course we need to get trajectories. Now, ideally, when you're getting trajectories to use with this metric, they should be qualitatively different in nature. You don't want the same trajectories multiple times, because then your ranking has no meaning because everything is the same. And these could be trajectories from partially trained policies. These could be trajectories from human demonstrations, kind of wherever you want to get trajectories can work. So in this example, let's imagine we have these 4 trajectories. The first is of successful driving. The second is of idle driving. So this is where the car is stopped. The third is a trajectory distribution, where there is a 90% chance you take the successful driving trajectory and a 10% chance you crash. And then the last is a crashing trajectory, where the car crashes. So given we have these trajectories, our next step is we need to rank them. So we first have them ranked from our human stakeholder, and then we have them ranked from our reward discount factor. So in this example, let's assume that our human ranks these trajectories top to bottom, best to worst. So they prefer successful driving over idle, over this probability distribution of successful versus crashing trajectories, and then crashing. So that's what our human stakeholder prefers. Now, next we can get the ranking from our reward discount. And what's nice is that a reward discount will naturally induce a set of rankings over trajectories if we just look at the expected returns. So we can look at the expected return for all the different trajectories and rank them, and that's how we can kind of get a ranking. So let's just say for this reward function that it has an expected return of 10 for successful driving, 0 for idle, 4 for this probability distribution of successful driving and crashing, and negative 50 for crashing. Now already, if we look at these 2 rankings side by side, we see that there's some misalignment, there's some mismatches in the ranking. So our human stakeholder has a higher ranking, would prefer to stay idle compared to this possibility of crashing in this tau success crash. Whereas we have the reverse set of preferences for this example reward discount factor. It's a little more it's a little less conservative, so it has a higher return or ranks higher this distribution compared to remaining idle. Okay, now the third step is from all of our ranked data, we have to get the number of concordant pairs, discordant pairs, and ties. So this is just a fancy way of saying how many times do the preferences match and how many times do they not match between our human and our reward. So from a ranking of 4 trajectories, this will induce 6 possible pairwise comparisons over the trajectories. And in this example, we saw that there were 5 times where the human and the reward agree on which trajectory is better. And as I alluded, there's 1 time where they don't agree, where our human is more risk averse, so would prefer staying idle over the possibility of crashing. Now, our next step, this is the last step, is that we just take all of this count information over a number of times we have matches and mismatches, and we just plug it into this very simple formula. This is a Kendall's tau B, and this is, again, just a simple ratio of the number of matches and not matches or mismatches, and also the number of ties. So it's very simple. And in this example, this would output a coefficient of 0.67, indicating that there is some misalignment in our reward function. So our reward function is not fully respecting our preferences, and we should likely kind of go back and adjust it. So now, hopefully, this trajectory alignment coefficient is a little more clear. So now I just want to discuss some nice properties for this metric. The first is that in this paper, we do prove that TAC, the trajectory alignment coefficient, is invariant to both potential-based reward shaping and positive linear transformations under some model start state conditions. So this is really good because what this tells us is that functionally equivalent reward functions will receive the same metric score, which is nice because, yeah, you don't want it to be the case where the same reward function would output different scores, because, yeah, that would lead to bad things. Yeah, so in the paper, there are several like proofs and theorems. So yeah, so if you're more of a theory person, yeah, I definitely recommend checking that out. Because yeah, for the rest of my talk, I'll be mainly focused on my empirical results, because yeah, I'm more of an empirical kind of gal. And then for second and third, unlike trial and error reward design, this metric does not require training of any RL algorithms. So that means it's less computationally expensive. And this also means that it is more applicable to the online RL setting because, again, it doesn't assume that you have to do some training ahead of time. Okay, I'll stop again to see if there are any questions about this metric before I kind of go on to the last topic for the talk.
How do you compare with humans? Like humans gives you some score or something?
Yeah,
Reward
human.
is numeric value, right?
Mm-hmm, mm-hmm.
Like how are you comparing whether they are of same rating or you know?
Yeah, so you will show the human. Let me go back to here. So yeah, you will show the human different trajectories. So this could be like a simple way is like say different videos of agent behavior, and then you ask them, can you rank these videos for me? Which one do you think is the best, the second best, third best, and the fourth best? And so that's our human preferences, and we're trying to see whether our reward function also has those same preferences. Do they also prefer successful driving over idle over kind of the third and fourth? So yeah, so the human isn't giving a scalar reward, the human is giving preferences, and this metric will quantify whether the reward function that, let's say, our practitioner comes up with, whether it respects the domain expert's preferences.
And RL policy will give you returns.
I'm sorry,
Right.
could you say that one more time?
You said that, yeah, I mean, RL policy gives you returns, right? Rewards
Yeah.
and return.
Yes.
So how are you comparing this, what do you call these preferences with a numeric value? Like which one is the
Yeah.
best? Like how do you relate these? These are quite, uh, different, right? Is I mean, preferences are not quantitative.
Yeah, so I think that's where we, in order to translate the returns of the trajectories, and like how we compare that to preferences is we will, like, returns can induce a set of preferences because now we can just say, okay, this reward function has a return of 10 for successful driving, whereas it has a return of 0 for idle. So it must prefer successful driving over idle because the return is higher. So we first kind of take these like scalar values and we can just rank those scalar values. And that's how we have a set of rankings under our reward function.
Okay, makes sense. All right.
Yeah, cool. Okay, yeah, so now we move on to the last part. So this is about how can we actually improve reward design? So yeah, I complained a lot and said this is really hard. So I'm trying to understand, is there a way that we can make this process easier for RL practitioners? Because especially if we want to use RL in more real world settings, we need to make it easier for us to design reward functions so that we can actually deploy RL. Now, I also introduced this metric, and I'm interested in seeing whether we can actually use that metric to help our practitioners during this process. And as a spoiler, if you stop paying attention for the rest of the talk, yes, you can use proposed metric, the trajectory alignment coefficient, to aid our practitioners during reward design. Now, to study this, we did a ethics-approved user study of 11 RL practitioners. And in this study, we focus on this domain called Hungry Thirsty. This is a very simple 4x4 grid world where the agent's goal is to go to the food state and eat as much as possible. However, if the agent becomes thirsty, the agent has to go to the water state and drink. But the agent will randomly become thirsty with a 10% probability. So the agent needs to kind of go back and forth between drinking and eating. Now, this may seem like a very simple environment because it is a very simple environment, but we particularly chose this because a past study found that all practitioners actually struggle to design reward functions in this domain. And that may seem a bit surprising, and it was surprising to me too, but it's also just crazy to think, like, if we're struggling to design reward functions in a grid world, like, how are we supposed to design reward functions for the tasks we actually care about? Yeah, so that was definitely interesting. But kind of as I've talked about, something we care about is this real world setting of domain expert collaborating with an R practitioner. But to kind of highlight that aspect, in our user study, we told our participants that they were to be designing a reward function with a domain expert of Hungry Thirsty. And at the beginning of the study, the users would see a series of video clips of different behaviors, and they also saw how the domain expert ranked these behaviors. And their first objective was to understand from these videos and the ranking, what does the domain expert like and dislike out of agent behavior in Hungry Thirsty? And the second objective was to perform reward selection. So first they had to understand, okay, what does my domain expert want in this environment? And then they were given 2 reward functions, and they had to choose which one they thought would solve the task and which one they thought would satisfy the domain expert. And this process was repeated 4 times. So they saw 4 different sets of reward function comparisons, and they had to choose which ones they thought were better or more appropriate for the task and the domain expert. So in this study, we aim to investigate 2 specific questions. The first is whether having access to this metric increased perceived benefit. So this is looking at the more qualitative experience of the user during reward design. So does it help them feel more confident in their decisions? Do they feel more successful, or do they feel like they had to use less effort? Kind of things of that nature. Now, the second question would focus more on like the practical side. This is asking, does having access to this metric actually help users in selecting the more performative reward function, such that if we actually did RL with this reward function, we'd have good policy learning kind of by the end of it. So this is more, again, more looking at does this reward function actually produce good agent behavior? Now, to study these 2 questions, we had users, like our participants, engage in reward selection under 3 conditions. The first is our alignment condition. So this is where they saw both reward functions, and they also saw the corresponding alignment score for those 2 reward functions. The second is very similar to the first, but this is our alignment and visualization condition. In this condition, the users had access to all the previous information, but they also had access to this visualization, which is a pairwise coordinate plot. And this is just showing the participant where the rankings differed between the domain expert and the reward function, because you don't get that information just by looking at the score alone. So this is telling you which trajectories had that mismatch. And lastly, we had our control condition. So this is our reward only condition where the users only had access to the reward function definitions and also the domain expert kind of preferences. So I also want to note that in this study, this was a within subject study. So every participant performed reward selection for all 3 conditions, but we did randomize the order to make it a fair comparison. Okay, I'll stop here just to see if anyone has any questions about the study design before I move on to the results.
What do you mean 11 RL practitioners over here? Like 11 algorithms?
No, so this means like 11 people who identified themselves as a person who does our research either in academia or in industry. So this is like 11 humans that do RL, and I'm asking them, can you design or pick a reward function for this domain?
You like sort of like a domain expert, you mean?
How should I say this? So maybe, so imagine, so there's a separate domain expert, and all they know is hungry, thirsty. All they know is about the environment. Like they don't know about reinforcement learning. And then I asked 11 different RL experts. So these are people who know about RL, but has like never seen hungry, thirsty before. And now they have to design a reward function for hungry, thirsty based on the preferences they see from the domain expert.
Oh, I see. Okay.
Yeah, so this is, I guess, focusing again on, is there a way, like if an R practitioner wants to design a reward function, is there a way that we can make it easier for them?
Mm-hmm. Makes sense.
Awesome.
Thanks.
Yeah. Okay, yeah, so now I'll move on to talking about the results. So the first is answering question 1, which again is looking at whether having access to this metric increased perceived benefit. And we measured this using a modified NASA TLX survey, which is a very commonly used survey for assessing perceived workload or perceived cognitive workload while you're doing a task. This bar plot is showing the average participant score for a subset of the survey questions. So the left is some of like the more negative feeling questions. So this is where we ask the user, okay, how much effort did you have to put in when you were choosing the reward functions? How much mental demand was required for selecting the reward functions? How stressed did you feel? Things like that. Where on the right, these are more of like the positive questions. How confident did you feel in your decision-making process? Ease of use means how easy was it for you to integrate the information from that condition into your decision-making process while you were selecting the reward functions. Now, the blue bars represent the control conditions, or the control condition, it was just one. And the purple and pink bars represent either of the alignment conditions. So these were the conditions where the user had access to the alignment score when they were choosing the reward functions. So what we see here is that if we kind of look on the left, that when users were in the alignment conditions, so again, the purple or pink, they reported like lower negative feelings. So reported lower feelings of stress, lower feelings of mental demand, like it required less from them, less effort, and lower overall workload. So overall, they felt like it took less effort for them to select these reward functions. So all that is good. Well, while at the same time, those users had reported higher positive feelings, so higher scores for these positive traits of confidence. They felt more confident in their reward selection, and they also felt it was easy to integrate the alignment information while they were making the decisions. So yeah, overall, this is positive. So now we have some evidence that when participants or RL practitioners are designing a reward function, if they have access to the metric, to help them during reward design, they feel like it's an easier process, which again is very important since it can often be something very hard to do. Now, moving on to our second and last question, this is looking at whether having access to the metric helped participants in choosing the more performative reward function. So could users or participants choose a reward function such that when we did training, RL training afterwards, we had good behaviors. So to measure this, we looked at the proportion of times users selected the reward that improved learning. So this is a heat map. I know it's a lot, but I'll break it down. So every row corresponds to data from a particular user, and every column corresponds to data across that condition. So the left is all the data from reward only, the middle is the reward and alignment, and then the right is having the alignment and the visualization. Now, if an entry is dark pink, that means that that user in that condition was able to select the policy improving reward function 100% of the time, so like 4 out of 4. If the entry is light pink, that means they did it at a rate of 75%. And if the entry is white, that means that they could only select the policy improving reward function at a rate of 50% or lower. So if we look at the plot in its entirety, so let's start with the left, we see that in the reward only condition, so when over 50% of participants in the reward only condition, they were unable to select the policy improving reward function at a rate better than random. This means that these participants might as well have closed their eyes and blindly picked a reward function, and they would have done just as well. Whereas when those same participants had access to the alignment scores, they were able to choose the policy improving reward function close to 100% of the time. And so this, of course, good because now it tells us that this metric can also help you select good reward functions that results in good behavior after the end of RL training. Yeah, so overall, if we put these two together, and again, we found in the first question that having access to our metric increases perceived benefit, so more it improves the qualitative experience of reward design. And second, having access to this metric also enables users or participants to select the policy improving reward functions. And this is really positive because remember, reward design is really hard. So if we can use this metric to make reward design easier, then that could be really impactful. Okay, so as I conclude, I just want to reiterate the main topics for today. I first started off by ranting about reward functions and how they're really hard. And I talked about what some of the aspects that make them challenging. I then proposed the trajectory alignment coefficient as one means to evaluate reward functions. And I ended with talking about how we can actually use that metric to help our practitioners actually design reward functions. And some of the things I'm currently exploring are looking at how we can use this metric to tune reward functions. So what I mean by this is that kind of in this study, in our user study, users had to just choose between two like fully specified reward functions. But this may not be as realistic. So I'm interested in seeing whether we can use the metric to have our practitioners design reward function from scratch, which is like a much harder task. And something else I'm interested in is looking at whether we can use this alignment metric for reward learning. So instead of manually designing reward functions, can we actually directly maximize this trajectory alignment coefficient so we can do learning instead of manually engineering them? Yeah, and before I finish, of course, I want to shout out my awesome collaborators. So my advisor, Matt Taylor from Alberta, Brad from UT Austin, Serena from Brown, Seorg from Princeton, and Carrick from Oracle. And yeah, that is the end of my talk. Thank you all for listening. If you have any questions, I can take them now. Here's a QR code from my paper website and also from my personal website.
Um, isn't that costly to uh, capture human preferences?
I'd say, yeah, so it can, I guess, yeah, it can be costly, but I guess I'd argue that it's less costly than the time that's necessary to design a reward function, I guess, without it. So my guess would be you'd save time and money by getting some human preferences up front and maybe attempting to use this metric to help you make the design the reward function instead of just trying to design it without any additional help.
Right. How did you collect these human preferences?
Yeah, so in this case, we use like what should I say, like an Oracle preferences. So we took the ground truth reward function from this environment and we just ranked trajectories according to that.
Right, makes sense.
Yeah.
But practically, in practice, it's costly, right? I mean, for any task, like in general.
Yeah, no, so in the work I'm currently doing, I'm using human preferences to label different trajectories. So no, it definitely, like, it does take time because I'm the person having to label them. So I do know it takes time, but yeah, I still think it's easier to label trajectories than to figure out like what function, like for what functions or weights you should be assigning like in your reward function. So I think that's still a harder task to accomplish, I guess I'd say.
Also, don't you think that um, uh, like if humans are involved in giving preferences, that would introduce some sort of bias? Depends on the group, right? Like who are labeling those preferences.
No, yeah, definitely. I guess here the bias is okay because these human preferences, like these should be coming from your domain expert, the person who knows who knows the most about this task. And so we want to actually make sure that our reward function is kind of biased to what they think is correct because like they know all about this task. So yeah, you do actually want it to be biased, right, in that case.
I mean,
I guess,
yeah, sorry. Go on.
Oh no, I was just gonna add, I guess this is less like what should I say? Like if we were like using preferences for like ChatGPT, where like if there was only one person giving preferences, but now like there's like a bunch of end users and they may all want different things from this system. I think in that type of context, then yeah, like the bias would have more of an impact because now there's like a bunch of people using your system who have different preferences. But like I guess in the context that I'm thinking about, at least maybe a group of domain experts, like they are the people that we want. We do want to be biased towards them because it's their preferences that we care about.
Yes. You mean a set of domain experts? Is it one expert you're targeting?
Yeah, so here it's one domain expert, but I can imagine like in future work thinking about, yeah, if there were multiple domain experts, like yeah, maybe we need to figure out how do we how can we respect a set? Because I can also think if you have like a very big problem, you may have multiple domain experts kind of for that task. So yeah, it could be the case that there could be many, and you have.
Yeah,
Mhm,
the reason why I was curious is because you can have multiple optimal policies, right?
mhm, mhm, mhm,
Even though you have, you know, same value function. It's like, you know, constant, like optimal value function would be unique, and probably your uh, policy would be, you know, you can have multiple optimal policies. Then every
mhm,
expert policy would be different from each other. Uh,
mhm.
so how would you sort of, uh, you know, scale from that?
Hmm. Yeah, I guess. Yeah, I haven't yet. I guess.
It's just
Yeah,
a thought.
figured.
It's just a thought. All right.
Oh no, but it's important. I mean, there's a lot of work on what's called pluralistic alignment. So like figuring out how to combine preferences from multiple people, especially if their preferences are conflicting. Um, yes, I don't think I have a great answer right now, but it's definitely an important topic that I need to think more about.
All right. Thanks.
Yeah.
Really, really interesting talk. Yeah.
Yeah, thanks so much for your questions.
Um, Anyone would like to ask questions? Yeah, sure.
Hello, am I audible?
Yes.
Actually, I have a more general question, not related to reinforcement learning.
Okay.
So I am kind of starting my journey in machine learning, and it's been around a year I have been learning. So since you are working on reinforcement learning,
Mm-hmm.
how do you choose which domain you like work on? So that's my question. Like, how do you choose a domain with NLP or reinforcement learning or some other uh, subdomain of machine learning? Like, how do you know that that's the field you should work on?
Oh, okay. So you're asking as a general question, like how did I figure out that I wanted to do RL out of like all the different topics you can explore like under AI? Is that what you're asking?
Right, right.
Oh, okay. No, yeah. So I have a background in psychology. That's what I did my undergrad in. So I chose reinforcement learning because it it seemed like one of the only, I guess, subfields of AI that I could kind of combine some of the prior things I learned about how humans learn. Um, and yeah, it just seemed like a cool avenue to study how we can have systems like I'll loosely say attempt to learn like humans learn. So yeah, that's why I chose reinforcement learning compared to like another sub area.
Okay, and for someone who is just beginning their machine learning journey,
Hmm.
um, currently I'm working on some NLP projects. So, should I keep working on NLP projects or should I explore other fields as well and then decide a domain which I might further work on or stick with? What would you suggest?
Um, yeah, I mean, I think like that's based on your interest. Like if you like NLP, like I think then you should, I guess, stick with it. There's also, I think there's probably some works that you can do to like combine NLP with RL. I mean, like I know that's like what's happening with like ChatGPT. I guess that's like those like LLMs are I guess within NLP and they use RL to kind of fine tune these large language models. Um, so I think there's ways if you're interested in RL to kind of do both. Um, I don't have a lot of background in NLP, I guess, to like thoroughly outline the pros and cons. But yeah, I guess RL in general, it seems like this is maybe a more general framework for like decision making. So yeah, I think if you're interested in in decision making, then this is something you can also explore. But if you're mainly interested in language and how you can process language, then yeah, I would say yeah, stick with NLP. But I think both are fine things to things to study. Um, And you can always change your mind. Like if you're early on in your kind of in your journey, it's okay if you do NLP and then you decide a year from now you want to do something else. Like that's totally okay.
Okay, thank you so much.
Yeah, thank you.
All right. Let's thank the speaker. Thanks for joining us today. It was fun.
Yeah, thank you
you.
so much.
Thank